Okay, and so far we haven't used Z-transforms for much because most of the really important things that we need it for, we need to be able to do inverse transforms for, and we kind of skipped over how to do that with Fourier, other than some simple cases. But now we're going to have to engage the full power of inverse transforms in order to solve all the more interesting problems that we have to solve. So, what are those problems? Well, we started listing them last time. And most particularly, if you want to do any kind of system analysis, that means we're either going to have to do a convolution to find a zero-state response, which transforms are better at. But then I need an inverse transform to get back to the time domain with my answer. If I want to find the unit sample response, well, that's easier to do by transforming the difference equation. But again, if I want a time domain solution, I'm going to need to use inverse transforms for that. So the first couple things that we would most likely want to use this for are things that require inverse transforms. We could do it with discrete time Fourier transforms or Z-transforms. Both are going to run into the same problem for doing inverse transforms if they're complicated functions. We're going to end up having to do some kind of partial fraction expansion probably. But the big deal, the big thing we came forward to do is doing system analysis, either relaxed system analysis, which we'll use inverse transforms for, or what we'll take up after the midterm exam is really the main good thing that we're going to get with Z-transforms that we couldn't do at Fourier, and that's take away this requirement for finding only zero-state responses in relaxed systems and finding total responses, including field of initial conditions. In the meantime, though, we certainly understand we can do convolutions, finding zero-state responses with transforms. We did it with discrete time Fourier transforms, but we're more likely to want to do them with Z-transforms. But again, that brings up the problem of easy to find the Z-transform of the answer I want, not so easy to get back to the time domain. I've got to do an inverse transform, which probably requires a couple steps. And again, the whole idea of transform kind of falls apart. We came here because it's easier to do the computation here in this transform domain. But if the way back to the time domain where I want it to be is too hard, then it wasn't worth it. So we're going to try to make that as easy as possible. And it is relatively easy. We're going to use lookup tables and a very scripted approach in partial fraction expansion that if you learn the mechanics once, you're good to go. And so that you can make that inverse transforming as easy as possible. So how do we do it? Well, pretty much the same list that we had for what I can do or what options I have to do a forward transform. I have the same options to do an inverse transform. The most straightforward is start with the definition. There's an equation that describes the forward Z transform, right? So we said x of z, that was a sum from n equals minus infinity to plus infinity of x of n, z to minus n. That's a transform definition. Well, there's a similar inverse transform definition equation that we could apply. But we're going to be more likely to want to make it easy by using known transform pairs. You want to look stuff up on the table. So put them in a form that look like some entries in the table. And if I can't find something that looks exactly like the table entry, well, then I'm going to see if there's a way I can manipulate it and look at how the properties of the transforms work. Look for things like time shifts or time compressions or time reversals, or anything that might modify my time function in a way that I can recognize in its Z-transform so that I can still use my tables along with the set of properties to do the inverse transformation. And together, these are going to be the nominal way to do it. But if I have an at all complicated function inverse transform, these tables tend to be very simple functions. And most of my things I need to inverse transforms, well, they're usually ratios of polynomials of z. And so I'm not going to be able to find a lot of the things I want to inverse transform directly in the table. I'm going to have to manipulate it and put it into that form. And that's where either long division or partial fractions come in. If I want to get analytical solutions, I'm going to pull in partial fraction expansion so that I get quantities, I get expressions, functions of z that I can look up in the table. If I just want individual sample values, well, I can actually take a shortcut in those and do long division and get those, and I do a transform. So same options we had for doing inverse Laplace transforms, same option we had for doing inverse continuous time Fourier transforms, inverse discrete time. They're all same options, same basic mechanics. There is one slight difference in doing inverse Z transforms in the mechanics of how we do it. And we'll look at how that is. So there's one slight twist that we have to apply that we didn't have to do with Laplace. So hopefully when we leave here today, we'll have that figured out, and the rest should be kind of a refresher on how we do these inverse transforms and partial fractions. So here's an example. We'll try this. H of z is 5z over z minus 0.1 squared. And we want to know if that's the transfer function of my system, we want to know what's its unit sample response, which happens to be the inverse transform of h of z. All right, we go up to our little handy dandy table, we say, what are my options here? Well, we can use a definition. And there it is. Here was the forward transform. That's not so bad. There's the inverse transform. That's looking a little scary. I got a z to the n minus 1. Okay, that's all right. H of z, dz. Oh, it's not a summation, it's an integral. Oh, wait a minute. It's a funny integral. It's got a circly thing on it. And then there's a j here. I don't like j's. I don't like circles on integrals. That's not your typical integral. That's a complex contour integral, the same kind of weird thing that showed up in the Laplace, inverse Laplace transform. Not good. So we cross that first option off the list. It's not going to be good. It's not going to be good. We're not going to do that. So, well, how many people have learned know how to do a complex contour integral? One. That's one more than most classes. Yeah, I usually learn that till you get to like grad school. And then they teach you, oh, it's some of the residues at all the poles, and okay. So it turns out the things that we're doing with partial fraction expansion and the mechanics that we teach you to do for that actually are the appropriate approach to use for solving a complex contour integral. But you don't need to know that, because it even makes sense mathematically when it's presented properly. So we're gonna forget about that. We're not gonna do that. We're gonna do it by some easier method, and just recognize that this sort of cookbook that we've got that we're working with, particularly when we're doing partial fraction expansion, actually does have a basis in complex contour integration. So it's all mathematically sound. It's all good. It's not just some trick up our sleeves. Instead, we want to look this stuff up in the table. So we get out a table, we get out our function. We'd like to look up over here on the transform side, find something that matches what we've got, and then just look over here and say, ah, voila, transform, let's go home. And so there's ours. See anything that looks like the one we want to inverse transform? Any row numbers that look good? Looks like I see 7. Yeah, 6 I heard first. There's some z squared and z7, z times alpha. Yeah, I think I'm going to have to go with that one. We're on line 7. So we can look that up and then match up terms. Okay, well, what's alpha? Alpha is the thing in the denominator after the minus sign. So 0.1 looks like alpha. And we've got a multiplier out in front. So we're going to need that. Okay. And I need an alpha in the numerator. So I need a 0.1 in the numerator, which means I'm going to have to turn 5 into 50 times 0.1. then I've got something that matches up the table, and I can just read off the answer. So again, we want to find something that's got the right basic form, then manipulate it so we can pick out each individual parameter from that transform table expression, and then construct the inverse transform. That's what we're going to want to do. All right. Remember when we came to Z-transforms, we said you got one new complication here, that there's two different functions that have the same Z-transform. This transform is shared by both this time function and this time function. One of them that's causal, one of them that's anti-causal. And so technically, if I give you something in inverse transform, there's two possible results in the time domain. And so I got to tell you one more thing, one more piece of information. I either got to tell you, here's the transform and this is the region of convergence, so I know which one to choose. Or give me a transform and tell me either, is it a causal system or causal signal or a stable one? You give me either of those two pieces of information, then I can infer which one it's got to be. Right? So in this case, if we inverse transform this, we have two options, a causal option and an anti-causal option. Pretty rare someone's going to walk up to you in the street and say, you know, that thing I want you to transform, the region of convergence is from Z equals 0.5 out there. Most people don't carry regions of convergence around in their pocket. So, more likely they got to tell you it's causal. All right, they tell you it's causal. Which one is it, left or right? Got to be this one. This is a causal function. This one's an anti-causal function. So, if I told you it's causal, it's got to be that one. What if I just told you it's stable? Could I tell which one it is then? Could I tell which one of these, if I said there's a transform and it's a stable system, and I say I've got these two options, which one am I going to choose and why? And there's a couple of these. There's a couple of answers. But think about what you know about stability. You want to take a shot? Okay, I'll help you out. Where's the poles of this one? Where do the poles live? At 0.1? Two of them at Z equals 0.1, right? So the real part, the imaginary part, so I got two poles at Z equals plus 0.1. Okay. Now if I tell you I have a stable system, do I know if it's causal or anti-causal? And with causal, okay. How can I put those two pieces of information together? That's my pole, and the system is causal. To say, or excuse me, that's where my pole is, and the system is stable, and therefore I know it's causal. The poles are all inside the unit circle. So that's the requirement I had for a stable system. If it was causal, all the poles had to be inside the unit circle. Or the fancy way of saying that is the region of convergence, which is defined by the outermost pole here, has to include the unit circle. And so it had to be a causal system. To have an outward-facing region of convergence to include the unit circle. Or the stability requirement for causal systems, all the poles have to be inside the unit circle. If those poles were out here, and I told you it was stable, then it has to be an anti-causal system. You have to have regions of convergence to go inward. But as you probably would guess, the most likely case we're going to be dealing with causal systems, so they'll have causal unit sample responses. We're going to be dealing with stable systems because unstable ones aren't that interesting to us. We try not to design those. So pretty much the causal case will be what we're after. So the other way to tell too is this function 0.1 to the n u of n, right, that's a dying exponential going positive, right? This one, 0.1 to the n where n is negative, what's that doing? Is that shrinking or growing? That's growing, going off this way. And so I have a unbounded unit sample response. It's going off to infinity, and I need an absolutely summable unit sample response to have a stable system. So that would also argue it can't be this one. All right. So again, usually we're not going to worry about that, but just for keep the mathematicians happy, we do have a way to say we're going to pick out the causal form because we're usually dealing with causal and stable systems. Okay, so different one. There's a h of z 5z to the minus 2 over z minus z squared. Now, which one are we going to pick out of the table? Z squared, looking for z squared. So there's lots of z squared. There's a z squared quantity there, z squared quantity there. But I have a z to the first power in the numerator. I don't like that. I'm going to z to the minus 2 here. So this is a more typical case where you're not going to be able to just look up the answer. You're going to have to manipulate this a little bit so that it looks like that. All right. Well, I would know what the z transform was if that was a 5z over z minus 0.1 squared. That one I could just look up in the table, right? That one I would have been happy with. So how do I make this look like that? I think if I multiply by z to the minus 3 maybe, then I get something that's equivalent. And that's where we pull out the properties and say, the property, it takes my transform and multiplies it by z. Ah, there it is. It's a time shift. So if you've got the wrong power of z in the numerator, look out, you probably have a time shift going on. And so, okay, so what we did there, we kind of manipulate this so that it looks like a form that's in the original table, this guy, and whatever we need to do to fix it up, put that aside and see if that relates to a property, which in this case it does. And so the way we would inverse transform this is let's inverse transform this part we know, and then apply the property that's implied by this extra term we have out there. So this simply inverse transforms to the answer we had before, 50n times 0.1 to the n u of n. This multiplying by z in the z domain implies we're doing a shift by 3 in the time domain. So everywhere there's an n, we have to replace that n with n minus 3, including the u of n, including the exponent. So, as often happens, we don't have exactly the form we want in the table. We've got to apply a property to make it so. Questions on that? Make sense? Again, we had the same issues when you were doing Laplace transform, inverse transforms in 228. Same kind of things we've got to deal with here. Now, if you happen to be inverse transforming a finite sequence, I've got one like this. Here's a polynomial in z. It's not a ratio of polynomials like most of them are. This would actually turn out to be the transfer function for an FIR filter. There's no denominator term. And this we could simply transform term by term, the way we were transforming difference equations to derive the transfer function. Right? So we just, because z transforms are linear operators, if I sum things up in the z domain, I sum them up in the time domain. So we simply inverse transform each one and recognize powers of z as shifts again. So this 1/2 times z squared, well, the 1/2 comes across as a 1/2 times deltas of n, and the z squared implies a shift by 2, plus 2. Likewise, this minus 5z would be inverse transformed to minus 5 times delta of n and apply a time shift of plus 1 to it. The 1 just transforms as delta sub n. 5z to the minus 1 is 5 delta of n minus 1, and then 1/2 delta of n minus 2. So again, the z's are shifts, and the coefficients come across as unit sample sequences. And this would be the case if we were inverse transforming a FIR filter's transfer function. So those aren't bad. Those are easy. Another reason we like FIR filters. So we only get, in this case, you could use shorthand. It's only got 5 samples. These are their sample values. Here's my n equals 0 term there. So is this a causal system, by the way? No. I've got a unit sample response that starts before n equals 0, so it's not causal. Oh, it's not causal. It has a finite impulse response. There's a finite number of non-zero samples. Is it a linear phase? Is it a linear phase FIR filter? How do I even recognize that? The number? Anybody recall? Magic is in here in these unit sample response values. We're looking for symmetry around the center. If they're even symmetric or odd symmetric around the center sample, that's a linear phase filter. These terms will transform the cosines or sines and we'll end up linear phases. And we like linear phase again because that implies that I'm time shifting all frequencies by an equal amount of time. I'm keeping everything aligned the same way, no matter what frequency it is. And that's so I'm not distorting the relative positions, relative phases of different frequencies. And that's something that FIR, this particular kind of FIR filter can do, but not other filters. Okay. All right, here's another one. Let's see. Now I'm in trouble because I've got a third order polynomial in the denominator, and there is nothing third order in my table. And now is when we have to get fancy. Now it's time to, and this is the typical case. When we're doing convolutions, when we're doing interesting transfer functions, they're going to be higher than second order usually. So I'm going to end up having to break this up. I'm going to have rational functions that I have to inverse transform. Any IIR filter is going to have that because it's got a rational transfer function. If all you want is the kind of sample values for the inverse transform, we can actually get them by executing what this says to do. Divide this polynomial by that polynomial and inverse transforming the result, just as we did with the FIR filter. Right? So if we took this expression divided by this polynomial, well, z squared minus z cubed goes into z squared. I need to multiply z cubed by z to the minus 1, so let me do that. I'll multiply all this by z to the minus 1 and get that term. Subtract them off, get a remainder. I've got 0.5z divided by z cubed. I'm going to need a z to the minus 2. Gives me that, a remainder. And I would actually have to keep going on forever because this is not going to determine an IIR. If I'm inverse transforming the transfer function of an IIR filter, I have an infinite sequence in the time domain. So this is never going to resolve. I could just keep going on for days. But the values that you get, this expression of z's, as that is the whole answer, I can inverse transform those one at a time and have a, well, z to the minus 1 is a delta of n minus 1. And 0.5 z to the minus 2 is 1/2 delta of n minus 2, and so on and so on. And we can get the sample values for the unit sample response, but we can't get a closed form expression. But if that's if you just need looking for a couple values, that's one way to get it. Usually that's not what we want. I mean, this is similar to what when you want to find the unit sample response for an IIR filter by the recursion method in the time domain. You can get sample values, you can't get a closed form solution. So instead, we're going to do partial fractions. Partial fraction expansion. This table is going to be the thing we use most often for inverse transforms. We're trying to break up our complicated function into a collection of ones of this style so that I can look up the answers over here. So we want to get them to match one of these, depending on if we have a first order pole or a second order pole or a higher order pole or complex conjugate poles. Yeah, we're going to need to break these up as sums of these kind of terms so that we can look up the answer over here and equate those and use the table for the inverse transform. All right. Well, yeah. No, I mean, they're still not better off than the integral. If partial fractions scare you, don't worry, it's not hard. And in fact, I'm going to show you my way, which is kind of the way based in the residue theory that the mathematics suggest. But you probably learned some other way. If your way works, as long as you get the right answer, I don't care. I'll show you why mine works algebraically, but you can choose whatever method that you're most comfortable with. So here's we'll take this through as an example, right? We're going to take this thing and we want to break it up into a collection of different terms that match up the ones in the table. And how we'll do that is we'll factor this polynomial denominator and come up with an individual term for each pole, basically, for each factor that we have in the denominator, and make a linear sum of those. Then the job of partial fractions becomes find the coefficient. And as long as these are a form that are in that inverse transform table, that partial fraction table. Now here's the twist that comes in with discrete time systems. Take a look at all those inverse transform forms. What can you tell me? What do they all have in common? Z minus alpha. There's a lot of Z minus alphas going on in there. Yeah. Yeah. So, well, except alpha sometimes is real, sometimes is complex. What else do you notice? They all have Z in the numerator. And normally when we do partial fractions, we don't have anything in the numerator other than a constant, a coefficient. So standard old-fashioned partial fractions isn't going to work for these. They're not going to give us the form that we need for this. And to be any good, I need the partial fraction thing that I expanded into to look like one of those terms in the table, or it's no good. And they all have Z's in the numerator. How do I solve that? I use a completely incredible, clever, brilliant way to get around this. If I need to partial fraction expand h of z, and I need z's in the numerator when I'm done, I'm not going to expand that. I'm going to expand another function that's h of z divided by z. I'm going to take a z and put it behind my back. Hide it while I do the partial fractions. And then get the partial fraction answer and say, ha ha, I wasn't trying to get that, I'm trying to get this one. Back in, we're done. And then I've got something that matches the table. Okay? So that's the trick. Oh, and by the way, I can't even get started unless the thing I want to partial fraction expand has to be strictly proper. Has to be a strictly proper rational function. If you remember that terminology, that means the z power in the numerator got to be less than the z power in the denominator. The order of the numerator must be less than the order of the denominator. Less than, not equal to. Now, so this dividing by z actually helps me. It brings the denominator up another power of z, or takes the numerator down by a power. So that helps me. But then that means that h of z, the thing I wanted originally, has got to start off as at least a proper rational function. So when I take the z away, I get a strictly proper one. Remember there, proper means they can be the same order. Strictly proper says the top's got to be less than the bottom. So if I start off with an h of z that's not proper, I'm stuck. Well, I have to do some long division first. Okay? So will partial fractions span not the thing we want the inverse transform of, but that divided by z, and then after the transform, we'll put the z's back in. We'll say, oh, h of z, the thing I want is that times z, so z, 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 and we're good to go. And these we can look up in the table. So that's the little brilliant strategy we have for dealing with that extra z in there. And the rest is all the same as it was in the class. But we'll review it quickly. So our method, whatever you got to inverse transform, first thing you do before you do anything else is take a z away. Take it out of the numerator. Take it down one order. Then factor the denominator, find where all the poles are. Give each pole its individual partial fraction term with an unknown coefficient in the numerator. And then the rest is just find the coefficient by whatever your favorite method is. My favorite method is, if I'm going to find K1, I'm going to take this thing I'm expanding, multiply it by the denominator that goes with K1, this pole term, and then evaluate that product at the value of z that makes that pole go to 0, so z equals P1, and that expression will give me K1. Now, this is already in your notes, I hope. If we literally do that algebraically, we take this function, we multiply it by z minus P1, so to bring that up here, these factors cancel, which leave me a more compact denominator. Well, actually, if we do that to this side as well, I multiply all these terms by z minus P1, z minus P1, z minus P1. And what happens? This one cancels out and leaves me just K1. This one, when I plug in z equals P1, every one of these has a z minus P1 in the numerator. They all go to 0. So you can see algebraically why this works. I'm just forcing all those other factors to go away so that I leave behind just the one coefficient. And when I do that for z minus P2, same thing happens, everything falls away except for K2, and so on and so on. You can also do this by equivalent numerators and denominators. You know, put these over a common denominator, it's got to match that. So the numerator's here, got to match the numerator there, and then you're matching up powers of z. That works too.
What happens if you have like double poles?
There's always special cases. Yes. So the same special cases we had before, complex conjugate poles, we've got to treat those slightly different. Multiple poles, got to treat those slightly different. Special cases. Right on time. If you have complex poles, well, good news. If we have one complex pole, we know there's a rule that says in order to have a real coefficient time function, like a real coefficient difference equation, that complex pole must appear with its conjugate, its complex conjugate. So if I have one of those, I'll certainly have a partial fraction term for that. I'll have a partial fraction term for complex conjugate. But the good news is their coefficients are going to be related. If the denominator terms are complex conjugates, so will be their coefficients. So I only have to solve for one of them. I'll solve for K1 the normal way, I'll solve for K2 the normal way, and then this one comes along for the ride. It's just the complex conjugate, meaning that anything that's J, we change signs on, anything that's spade, we change signs on. Now, we didn't really save anything because it turns out complex conjugate poles are going to transform together anyway. Right? Their inverse transforms when we have complex conjugate pairs are always cosines or cosine and sine combinations. They always come across together. So, but, you know, one less pole to solve for, one less partial fraction to do, that's kind of nice. Well, let's take an example through. of doing a zero-state response of a system, where we start off with the system being described as a pole zero diagram with one piece of information about frequency response, and I say, there it is, here's my system, and here's how we can find the magnitude, and I want to take this system, and I want to put it in this signal. I want to have to be in U of n, and I want you to tell me what comes out. So that's a cloaked way to say, I want you to do a convolution using transforms. So we need a transform for x of n, we need a transform for h of n, we need our h of z transfer function, then I can combine them to find the output transform, and then with inverse transforms with partial fractions. That's so we're doing this game, right? If the time function is the convolution of the input with the unit sample response, we transform that whole thing to the z domain. We end up multiplying the transforms and then inverse transforming that back to the time domain. All right. So first we need an h of z, then we need an x of z, then we need to multiply them, then we need a partial fraction expand and look up the results for the inverse transform. Still with me? Still waiting? Still out here? It's getting dark. Okay. First, let's do a little practice on recovering our pole zero diagram, our transfer function from the pole zero diagram. Where's the zeros? Z equals +1, and I've got poles. That's hard to read the fine print. Let's see. Looks like the poles are at +0.5, plus or minus j.5. So we can reconstruct the transfer function as the zero location, z minus 1. And the poles are z minus 1/2 plus j5, this guy, and minus at 1/2 minus j5. We use minus signs in there. And the other thing I can't get from directly from the pole zero diagram is there an unknown gain factor out in front. Okay, everybody, so you should be getting good at this by now. By all means, please, before the next week's exam, be good at this. You should be able to go forwards, backwards, left, right, with all these. So we combine those together, we get a transfer function that's k times z minus 1 over z squared minus z plus 0.5. And we solve for k, that's where I needed that extra piece of information. So somebody told us the frequency response at one value happens to be frequency f equals 1/2 equals 0.8. Okay. So at frequency 1/2, where am I in the z domain at f equals 1/2? I'm on the unit circle somewhere. Where am I? Where am I? Z equals what? J. Z equals j? I'm up here. Everybody agree? I'm not happy with that. Let's keep moving. Where am I? -1. How did you know that?
Because the whole, going around the circle, once is 1.
Once is 1, so halfway around is 1/2. Or, remember the angle is 2 pi f. We replace z with e to the j 2 pi f, so I need 2 pi f to be equal to 1/2. That means, or I need f to be 1/2, so I put 1/2 into 2 pi f, and I get, and then over here, an angle of pi. So yeah, so we're operating over here. So then that means I should be able to replace z equals -1. That's the same thing as h of f at f equals 1/2. So I can set that equal to 0.8. So the frequency response at f equals 1/2 is the same as the transfer function h of z evaluated at z equals -1. So I put -1 in for z there. Set that equal to 0.8 for the magnitude, and it turns out k is 1, so we can drop it. All right. Yeah, so that's the function, it turns out. That's what it would look like. It's an interesting function. It's a little batty. So here we go, we got h of z. All right, I got this one. I guess we need x of z next. There's our input signal. 1/2 to the n u of n. What's the z transform of that? Remember? It's an alpha to the n u of n. Its z transform is z over z minus alpha. So we just looked that up in the table. Now, y of z is just the product of those two. So I'll take x of z, that was z over z minus 1/2, multiply it by h of z, that was z minus 1 over these two guys, and I have my y of z. That's the answer. It's just in the wrong domain. I want a time function, not a z function. So we want to partial fraction expand this and get back to the time domain. Oh, no, I don't want to partial fraction expand this. I want to take a z away first. Let me take the z and hide it behind my back. And form the polynomial that we are going to partial fraction expand. So you notice I took the z away. And then let's express this as a sum of each of these pole terms. Where I have a complex conjugate pair, so I know their coefficients have to be complex conjugates as well. All right. The rest is just mechanics. We're going to solve for these using the standard old-fashioned partial fraction method. I'm going to take this whole thing, I'm going to multiply it by the z minus 0.5, which cancels out one of those guys, leaves me this, and I'm going to evaluate that quantity. I'm going to replace z with z equals plus 1/2 to make that go to 0. Wherever there's a z in here, I'm going to put, well, when you've got these complex conjugate terms, it's sometimes easier to put them back as a quadratic. So you can make it easy to plug in the powers of the z values. And everywhere there's a z, we put in 1/2, z we put in 1/2, z we put in 1/2, and just simplify down. It turns out a is minus 2. And b we solve the same way. Even though it's a complex quantity, we multiply this whole thing by its pole term, which eliminates one of the terms out of the denominator. And then we'll replace z with, well, the thing that makes this go to 0 would be plus 1/2 plus j5. So everywhere there's a z left in here, I put in 1/2 plus j5, 1/2 plus j5, 1/2 plus j5. And you get an s. You can combine real and imaginary parts in the numerator, real and imaginary parts in the denominator. And either in rectangular form or polar form, actually polar form is going to be easier to inverse transform, so I recommend you do that. You can come up with what's the value of b. And then I know this other one is just the complex conjugate of this. The way I get the conjugate is I change the sign of the phase, everything else stays the same. And then we're done. So we have that. And then we have our coefficients, we're all set to go. So we've got a partial fraction expansion for not the thing we want, but this other thing. I'll bring back out that z, put it in all those terms, and now I've got the thing that I needed, a partial fraction expansion in a form that I can look up in tables. So this one's easy, it looks like that, it's an exponential term. This one looks like this term, and then I've just got to be very careful about matching things up. So what I'm going to do is say, this term up here has an e to the plus j angle. Let me find which term has e to the plus j angle. That's this one. So now this I'm going to equate to this. I see z, I see k, looks like square root of 2. B looks like minus pi over 4. Alpha looks like 1 over square root of 2. And omega looks like plus pi over 4. If I didn't match things up, I might have gotten the wrong sign on my phases, so be careful how you do that. So k was that, alpha was that, omega was the positive one, and b was minus pi over 4. So knowing that, I just plug in those values into inverse transform form, and we can inverse transform using the table. And get this form. Okay, so just be careful with the matchup. That's the hardest part there. Ooh, which part of this is the forced response? The 1/2 to the n u of n, or this cosine thing? I hear votes for everything. How can I tell? What am I looking for? We want to match the input signal. The input signal was 1/2 to the n u of n, so that would be the forced response. Has the same form, and this would be the natural response. Or the other dead giveaway was this partial fraction term came from the input signals transform, created this term, must be the forced response. Okay, real quickly. What if you have repeated poles, like I have a squared or a cubic or whatever in the denominator? Well, same deal that we had in Laplace transforms. We're gonna, for every pole, I need an individual partial fraction expansion term. So if I have a square term here, I need 2 poles over here in the expansion. One that has the square term with it, one that has a first order. So if I have a cubic here, I'm going to have 3 terms: a cubic, a square, and first order. So we have 1 term for every pole that appears. And we descend keep bringing the exponent down until we get to a first order pole. Finding the coefficient that goes with the highest order term, this A0 coefficient, we just do the same old way. We take this whole thing raised to the highest power, multiply that by the rest of the function, evaluate it at z equals the pole, and the algebra says we end up with just A0. The rest of them are harder to get. For the rest of them, we've got to start taking derivatives. Take derivatives of that original product, the thing we were trying to transform, times the pole term raised to the full power that it had. If it was a square, we keep the square in there. If it was a cubic, we keep the cubic in there. For the first term, we take a first derivative of that, evaluate that at the same pole term, and we get our A1. If you have more and more, the general form is take the function, multiply it by the pole term at the highest power, replace z with that the pole value that makes it equal to 0. Keep taking derivatives, successive derivatives of that for each coefficient, but watch out, there's a 1 over n factorial out in front. So when I start getting to cubics, then I have a 1 over 2 factorial. And then the fourth order term has a 1 over 3 factorial, and on and on and on. So here's a quick example of that. If you've got a system with these 2 poles, and you put in a transform of an input signal that has a pole in the same location, you get up with a square in the denominator. Take away a power of z from the numerator. Partial fraction expand this, so we have a z minus 1 squared term and a z minus 1 without the squared first order term. The k we do the normal way, the a we do the normal way. The A1 is a different one. We take this original product, take its first derivative with respect to z, set z equals plus 1, and get that term. Turns out to be 3/4. And we just keep successively doing that until it's not even higher order. Okay. So that would partial fraction expand, and those square terms, cubics, tend to be n times terms. Okay. Need to let you go. We'll see you on Monday. Work on that homework. Give it a good try, and we'll check out the answers and get ready for the midterm on Monday.